Good afternoon, everybody. My name is Angelica Bain, and I'm a sophomore at Washington Liberty High School. This year, I decided to study the effect of different blue light mitigation techniques on LED blue light radiance. It's already well established, especially with the recent rise of research, that exposure to blue wavelength light from LED sources increases risks for negative health effects. And these effects can range from ocular effects like macular degeneration to immunological effects like messing up the circadian rhythm in your sleep cycle. But with all this research, there's still not that much data about preventing these risks. Many devices and techniques claim to reduce blue light, but they lack validating quantitative measurements of relative effectiveness. This project is based off my last year's project, where I tested the effect of app color scheme on LED blue light irradiance, where I found that dark modes have a dramatic impact on blue irradiance dosages. I decided on my project because I recognize that dark mode still isn't a perfect solution. It's not available on every app and platform, even though most are working on it. And this expansion allows me to perform a more comprehensive comparison of multiple mitigation techniques in response to many of the questions and suggestions I received from last year. This year, I aim to accurately measure the relative effectiveness of different mitigation techniques by testing different blue light blocking methods' impact on the amount of blue light energy emitted from LED screens and smartphones. And as a member of a generation of digital natives, I'm deeply personally concerned about the long-term health consequences for myself as well as my peers. And I really hope to help people make informed choices on how to reduce the risk of harm to their eyes, brains, and immune systems. The independent variable in my experiment was the blue light mitigation techniques, and the different levels for this was having no change, using night shift mode, which is an Apple feature that changes the screen palette to have more of a yellow tint, a Reticare screen filter, and gamma ray optics glasses, and I took 10 trials of each. One of the weaknesses of my project design lied in the small amount of different blue light mitigation techniques. Only testing 3 methods is not an accurate representation of the hundreds of products out on the market. The data collected were measurements of the light energy within blue light wavelengths, which is from 450 to 490 nanometers, and this was measured as relative irradiance in watts over meters squared. Some of the most important constants were the device tested, which is an iPhone 11, the brightness of the device, which was set to the maximum so I could get the strongest reading, the device used for testing, which was a Spectrix USB VJAS, or visible light spectrometer, as well as the distance from the smartphone to the spectrometer, which was 5 millimeters. I hypothesized that if blue light mitigation techniques are tested for the amount of blue light relative irradiance using a spectrometer, then the night shift mode will prove to be the most effective. I based my hypothesis off a research essay which documented the use of physical optical features and software-based filters for the purpose of blocking blue light, and software-based filters proved to be more effective. I used Spectrix open source software, which showed the measured energy levels at visible light wavelengths. The phone was mounted in a cardboard box, so it was perpendicular to the light collecting sensor from a constant distance. On the top left, I included a digital diagram of how the experiment was set up. And on the bottom left is an image also replicating the experimental setup. But please note that I was tilting the phone for a better and easier to understand visual of the phone screen. And here's the spectrometer fiber tip. And this distance was not the same, just to view it. One of the most helpful resources I had while designing my project was last year's science fair and the feedback I received. With these suggestions, I was able to create a more efficient and effective setup to get more intense readings, as well as obtain better equipment to have more accurate results. One constraint that I encountered last year as well as this year was this lack of precision in spectrometer. This year I had an upgrade of equipment, but it's still not perfect. And for future projects, a higher quality spectrometer would be beneficial for improving the results and data even farther. And for risk, when working with fiber optic cables, it's extremely important to not look down them, in case there's sometimes invisible laser light that could harm the eyes. The fiber I used was a receiver, but still out of an abundance of caution, I followed the guidelines and did not look directly down the cable. One of the strengths of my data was the mass amount I collected. In just the blue wavelengths, I collected around 16,000 data points. This allowed me to have a more accurate result and just allowed me to feel really confident about my results as well. A weakness that did come with this, though, was compiling this into a summative data table. It was still long and kind of scary, to be honest. So I found that the best course of action was to create a line graph. The x-axis is the set of blue light wavelengths, and the y-axis is the amount of energy emitted in relative irradiance. This blue line represents the control group, and this prominent difference between it and the blue light mitigation groups really proved that it did have an effect. But the most unexpected thing I noticed was this trend that appeared in all the data sets, and that the values became lower as the wavelengths progressed past the peak of the blue light wavelengths. And at first I was confused and worried that my data had an error, but upon further research, I found that this can be explained by the shift of colors and the cyan wavelength starting. To test the degree of variability, I conducted an ANOVA test. The standard is that if an ANOVA test results in a p-value of less than 0.05, then the results are statistically significant. My ANOVA test resulted in a p-value of 1.10 times 10 to the negative 15th power. And this minuscule number supports that the levels of the independent variable were statistically different from one another. I also calculated standard deviation, and this did not go above 1.7. And for most data sets, it was even lower, which shows that it was very little variability. And to create a more accurate understanding, and I didn't want to solely rely on the ANOVA test, so I conducted a t-test with each of the independent variables in the control. And all of these tests had extremely small numbers as a result, and that really helped support that my data was statistically valid. And my results also support what other scientists have found, which is that LED light can be combated by mitigation techniques. By contrast, the control set emitted on average 220% more light than the blue light blocking data sets. And the reason for this large decrease in energy is because all the products used to mitigate blue light had a yellow tint, and this contrasts the blue. And all of the mitigation techniques proved to be very effective, but I found the most effective way to protect eyes is the use of a blue light blocking screen filter. However, my hypothesis predicting that night shift mode would be the most effective mitigation techniques was rejected, but all of the mitigation techniques were super effective, and this led me to reject my null hypothesis, which states that blue light mitigation techniques would have no effect. Some of the limitations of my data was that only one device was tested. Different devices emit light slightly differently, so if more devices were tested, I would have a more accurate result that reflected a more representative sample of products. I had the same limitation when selecting the screen filter and the glasses I would use. And the market features tons of products, so by only selecting specific brands and products, I was not able to capture an accurate sample of the market. But these limitations helped me brainstorm how I could improve my project for the following years. One idea was I could study pages of device screens where the user primarily spends time, like Gmail or Zoom. I could also expand the devices I test to laptops, since many overlook using blue light blocking methods on computers, even though we use them every day. And another idea is to test different combinations of blue light mitigation techniques when used concurrently. My current results can be used by technology users to help guide their screen usage and their decisions about mitigation techniques that they might invest their time and money in. They can also be used by other stakeholders like technology manufacturers, policymakers, educators, and employers, who may consider results as an important element when deciding on recommendations for screen usage. But the most important thing I learned was that when it comes to protecting the eyes, doing any type of protection is significant and beneficial. Thank you so much for listening.